So the last time we talked about the Gibbs free energy master equation, which states that delta G equals delta H minus T delta S. So we are combining an enthalpic term and an entropic term, and entropy has to be multiplied by temperature. The sum of these, okay, or we're actually subtracting them, gives you Gibbs free energy of a process, okay, the delta G of a process. And we had talked about how in different scenarios, depending on the sign of delta H or delta S, delta G would be always spontaneous, so definitely negative means always spontaneous, definitely positive, never spontaneous. And in situations where both enthalpy and entropy changes are negative, there's a question mark because the reaction is spontaneous when this term is allowed to dominate, so when this term is small. So we call that spontaneous at low temperature, or you can also say that it's enthalpy driven because this negative term has to dominate. And it's the opposite situation when both enthalpy and entropy changes are positive. In that case, if you want Gibbs free energy to be negative, this term has to be large and positive so that when you subtract it, you end up with a negative. So we call that spontaneous at high temperature, or spontaneous when T is big, or entropy driven because spontaneous when delta S is big and positive. So I want to give you an example of using these ideas. Let's take the Haber-Bosch process. This is a process that's used to manufacture ammonia. And ammonia is a really key ingredient in fertilizer, so this industrial process is really responsible for feeding much of the globe. In this chemical reaction, we take diatomic nitrogen and react it with 3 moles of diatomic hydrogen to make 2 moles of ammonia, and everything is in the gas phase. Now, you could calculate the delta H of the reactions by looking up the heats of formation in a table as negative 93 kilojoules per mole. Here I'm just going to give you these values. Same for the delta S of the reaction, negative 198 joules per mole Kelvin. You can actually calculate this by looking up entropies of formation in your book's appendix. So my question for you, since the sign of both of these is negative, we are in a situation where it's not necessarily clear that this reaction is going to be forward spontaneous. So it's in the category that is going to be spontaneous at low temperature. And my question for you is, at what temperature will this reaction be spontaneous? So we have to take these values and plug them into the master equation. And we have to find, for delta G, the border between positive, which would be non-spontaneous, and negative, which would be spontaneous. What is the border of positive and negative? Why, it's 0, of course. So 0 is the border between positive and negative. So in order to tell what temperature this reaction will be spontaneous at, I'm going to plug 0 in for delta G. And then I can plug in the values for delta H and delta S as follows. So I have negative 93 kilojoules per mole minus T times delta S. Now you have to make sure that the units match. So delta H is in kilojoules per mole typically, delta S in joule per mole Kelvin. So here, to make sure that the units match, I just converted delta S to kilojoules per mole Kelvin because the units must match if we're doing this arithmetic. Now I can solve for T. Doing the algebra, I bring this over to the other side. Solving for T, I find that T is 470. What unit? It takes the Kelvin unit because that's in the denominator of the entropy. 470 Kelvin. Subtracting 273 from that, the Celsius temperature would be 197 degrees Celsius, which is pretty hot. Okay, this is quite a bit above the boiling point of water, for example. Now we have to remember that this is a reaction that is going to be spontaneous at low temperature. It's an enthalpy-driven reaction because enthalpy is the negative term. That means that the reaction will be spontaneous below this temperature, not above it, but below it, because it's an enthalpy-driven reaction. So let's do a similar problem, looking at a second example. Is the following process spontaneous? Here I'm giving you delta H and delta S values that are both positive, 10 kilojoules and plus 40 joules per Kelvin, figure per mole of the process. And the temperature is, say, 200 Kelvin. Well, all you got to do is plug these three values into our master equation to calculate delta G. Make sure you convert the unit. In this case, I'm going to convert everything to joules. It's just easier. 10 kilojoules becomes 10,000 joules minus 200 Kelvin times 40 joules per Kelvin. When you do the arithmetic, you find that the delta G is equal to 2,000 joules, or 2 kilojoules. This is positive, so it's not spontaneous, or reverse spontaneous, or unfavorable. So the question becomes, at what temperature would it be spontaneous? This is a reaction that would be entropy driven, because entropy is positive, and when we plug a positive value in here, temperature is always positive in kelvins. This term has to be large enough for the negative to take precedence and give us spontaneity. So, once again, to find the border between positive and negative, we set delta G equal to 0, and then we can plug in our values for delta H and delta S. What I'm going to do is just taking this relationship, I am going to rearrange the equation to solve for T. So just doing the algebra to rearrange this equation, T equals delta H over delta S. Plugging in our values in joules, 10,000 joules over 40 joules per Kelvin, that gives me a temperature of 250 Kelvin. Now, this is an entropy-driven reaction. So that means in this case, the reaction is going to be spontaneous above this temperature because the entropic term needs to dominate if you want it to be spontaneous. Okay, so I hope all of that made sense. And in the next lecture, we will talk more about calculating delta G of a reaction from the standard free energies of formation.